Today, I will talk to you about my vision for how energy-efficient hardware accelerators will be critical to enabling a wide range of imaging and vision applications on mobile devices. So it is projected that 1.2 trillion photos are going to be taken in 2018. And 85% of these photos are going to be taken by cell phones and not by traditional digital cameras. Moreover, the imaging that we do today with these cell phones isn't what it used to be 5 years ago. The final image that we see today is not merely a projection of light from the scene onto a sensor, but it actually results from a deep calculation. For example, if the sensor captures a blurred image due to camera shake, we can computationally deblur it and produce a sharp image. However, when this deblurring algorithm, for example, is implemented on a mobile CPU, it takes 13 minutes to deblur one single image frame, which translates to 2,000 joules of energy. So to understand how much 2,000 joules of energy is, if you consider a cell phone battery of 1,800 milliampere hours, it means that your phone will be dead after deblurring only 10 photos. So my approach to solving this problem has been to design dedicated, energy-efficient hardware accelerators for complex applications. For example, in case of deblurring, using the accelerator, we can bring down the energy to 0.1 joules per frame, which means that now you can deblur thousands of photos without exhausting your battery life. So therefore, accelerators such as these are critical to enabling new applications on consumer phones. So now I'm going to give an application-level highlight of my work, and then I will delve deeper into one specific example and conclude again with a high-level overview. So to put things into perspective, let's visualize where implementation of vision and imaging algorithms lie on this chart. So this chart is basically plotting the energy taken to do an algorithm versus the execution time of that algorithm. So basically, where we want to be, and both of the axes are on a log scale, where we want to be is down in this green region, where you have a small amount of energy so that you don't exhaust your battery life, and small amount of execution time so that you can see results in real time. So if you look at one example, for example, video decoding, now this is one application which has been heavily optimized and has dedicated hardware on each and every cell phone. So basically, every time you use your phone to see a YouTube video, you have a dedicated hardware accelerator that's decoding the bits and giving you an image frame. So this is heavily optimized, and it lies in this green area. But something like image deblurring that we saw earlier, on a mobile implementation, it lies all the way over there in this red region. So basically, this is unacceptable for a mobile implementation. However, if you design an accelerator, you can bring this algorithm all the way down to the green region. Similarly, you have other applications. For example, another application that I've worked on is high dynamic range imaging, which is basically a method to enhance image quality by combining images which have been taken with different exposures together into one single image. So if you do a mobile implementation of this, it lies somewhere over here. But with a dedicated accelerator, you can bring it down all the way deeper into the green region. There are more algorithms that benefit a lot from hardware acceleration. For example, there's some recent research at MIT where they've designed an algorithm for motion magnification. So basically, you have a video in which there are some tiny motions that are imperceptible to the eye, but you can algorithmically enhance those motions so that they become perceptible to the eye. For example, in this case, you can actually see the baby breathing after the video has gone through motion magnification. So an implementation of this lies somewhere over here on a mobile phone, but with an accelerator, you can bring it all the way down over here into the green region. So basically, what I want to come across is that you can enable orders of magnitude improvement in energy and orders of magnitude improvement in execution time if you design dedicated hardware accelerators. So far, the algorithms that I showed you were more of an image processing type. So what you're trying to do is you want to try to enhance the image or the video quality in some way. But there's also another kind of algorithms which do more of image understanding. So all of your image recognition, object recognition, neural network type algorithms lie in this class. And there's also work on designing hardware accelerators for these so that you can do these algorithms in real time and with low energy. So with that preview, I will give you one specific example. So there are a bunch of applications that I've worked on: image deblurring, HDR, motion magnification. And I'll give you a sense of what it takes to design these hardware accelerators for some of these imaging applications. For each of these, you can get orders of magnitude reduction in runtime and energy when you build dedicated hardware. So let's start with deblurring. So camera shake is actually the leading cause of blur in cell phone camera images. And this is especially unfortunate when you don't have the opportunity to recapture that photo and the moment is basically lost forever. Now, to deblur an image, one needs to know the trajectory of the camera when the image was captured. And this trajectory is called the blur kernel. So normally, this blur kernel is very hard to infer visually, but I will give you an example where you can see it visually. So in this special case, you can actually visualize the blur kernel by carefully looking at the trajectory of a point source of light in the image. So this basically shows you the trajectory that the camera took while you were taking that shot, because your hand was shaking. So in general, you don't have these point sources of light in images, so you have to sort of infer this kernel computationally from the image. And so your deblurring problem reduces to algorithmically figuring out what this motion or blur kernel is, and then deconvolving that original image with this blur kernel to give you the output sharp image. And in this algorithm, most of the time is spent in estimating what this kernel is, and very small amount of time is actually spent on doing the final deconvolution. So we decided, OK, kernel estimation is our target for acceleration. Now, there are several ways of doing kernel estimation, and one very accurate algorithm is based on an expectation maximization type algorithm. We're not going to go into the details of what the algorithm does, but I will give you a very high-level picture of what it's trying to do. So how does this algorithm work? Your blurred image can be represented as a convolution of your kernel and a sharp image, which you do not know. So basically, if we had either the kernel or the sharp image, you could infer the other because you can solve this math problem. But we don't have any of them. So we basically do the next best thing. We make a random guess for the kernel, and then we use this to compute a candidate sharp image. And this step is called the E step. And then this sharp image is not going to be the best possible sharp image, but it's going to be better than what you had before. So what you can do is you can use this to refine your kernel estimate. And then you can, and this is called M step. And you can do this iteratively till you get better and better kernels at each step. Now, the reason this works is because at each step, you enforce some more constraints on this problem, such that the sharp image that you get actually converges towards naturally looking sharp images. So it's not as simple. There's extra constraints that actually enforce this algorithm to converge. So when you design a hardware architecture for this, you basically have to design modules that can solve the different problems, the math problems that exist in these different portions of the algorithm. And so there's a whole bunch of blocks that you design, but I can't go through all of them. So let's focus on the computations that happen in one of the blocks. So for example, let's look at M step for now. In M step, what you do is you have a candidate sharp image, and you're using it to refine your kernel estimate. And so if you work through the math, it boils down to solving some sort of quadratic programs. And so essentially, you can write your M step mathematically as finding a k that minimizes this quadratic function subject to some constraints. And the quadratic function, the coefficient matrices A and B of that quadratic function are determined by the sharp image that you already have. So the way you compute these coefficient matrices, for example, the way you compute A, is that you take your sharp image S, you shift it by some amount x1, y1, and you shift it by another amount x2, y2, and you multiply and accumulate in some area. So basically, what we are trying to see is, given this algorithm, what's the basic computation that we are trying to do? And the basic computation that we are trying to do is some sort of correlation of images. So to give you a simple example and walk you through this computation, let's look at this matrix A. So this is that A matrix which was inside that kernel quadratic program. And for a small kernel, 3 cross 3 kernel, you have a 9 cross 9 matrix. And the way you compute one entry of that matrix is that you take your n cross n sharp image, you shift it by some amount. So 1 cross 1 corresponds to the index on the y-axis, and 0 cross 1 corresponds to the index on the x-axis. So you take your sharp image, you move it by these two different shifts, and in the area in which it overlaps, you multiply and accumulate. And that multiply and accumulate gives you one value, which is the value at this yellow dot. And so now if you do this naively, you're going to take order m to the 4 n to the square computation time, because you're computing m to the 4 elements of this correlation matrix for an m cross m kernel. And then each element takes you n squared time, because you're doing n squared multiplies and n squared adds. But we can do better. So the first step in designing any hardware accelerator is basically break down your algorithm and see where is it that you can reuse computation and extracting that out. So for example, what we observe is that for all the pixels along any diagonal of this matrix, the relative shift between the two images that you're multiplying remains the same. So basically, what you're doing is that you're overlapping the same two pixels, you're multiplying the same two pixels, you're just accumulating in different rectangles. And so you don't necessarily have to do this computation naively and repeat it over and over for each entry. You can do that multiply once, compute some sort of an integral image of that, and then compute the areas of these different rectangles in some constant time operation. So basically, the crux is that the first step in designing hardware accelerators is to analyze your algorithm and see what computation can be reused in the process of that algorithm. So you can reuse this computation. So that's good. And this makes this algorithm, instead of m to the 4 n squared, it makes it m squared n squared. So that's a big speed up. But then you don't necessarily have to stop there, because hardware gives you more advantages. So what hardware allows you to do is that you don't have like one CPU where you can do one of these computations at a time. You can potentially have as many number of parallel processing elements as you want. And so here, in this case, we decided to have 6 processing elements, which gives you basically a 6x improvement in your runtime. But then you also have to think about how to feed all these processing elements. And so what you end up doing is you design some sort of a memory hierarchy that lets you feed all of these processing elements in parallel. So we're not going to go into details, but basically the crux is that, one, you change your algorithm to find computations that can be reused. You take the advantage of being able to have as much parallelism as you want to reduce your runtime and increase energy efficiency. And then you have the flexibility of designing your memory system such that it can feed all of those parallel elements at the same time. And that leads to energy efficiency and runtime improvement. So let's look at another example. So now, after you do that, you have this A matrix, and you actually have to solve this program. And you do some sort of a conjugate gradient type algorithm. But the main computation in this algorithm is basically some sort of matrix vector multiply. So there's a whole bunch of math, but essentially the most computationally intensive part is a matrix vector multiply. But then again, what we notice is that you have these matrix vector multiplies, but your vector, since it's an iterative algorithm, your vector is not updating at all of the indices at a time. So for example, in this case, say the vector updates only at one index. You don't have to naively do the full matrix vector multiply again. What you can do is you can only load the first column of A, multiply it with the delta that has changed in the vector x, and compute your final result. So basically, you're taking advantage of sparsity in the updates to x to reduce the amount of computation. When you're using traditional hardware, sometimes it is very expensive to take advantage of this sparsity. But if you have dedicated hardware at your disposal, you can design your memory system such that it works efficiently with this sparsity. So basically, you can take advantage of reducing computations in ways that are not possible in a traditional setting. So this, on an average, we see that this saves 10x compute and 11x compute in memory. So we incorporated all of these techniques. We actually made a chip for this, and this is a die photo of the chip that we made. And we can actually use it to deblur images. So for example, this shows the results. So there's a blurred image on the left. You estimated the kernel that's on the right, and then when you use it to deblur, you get the sharp image. So it actually works. And then when you measure the performance and runtime, you see that you get a two orders of magnitude reduction in runtime and 3 orders of magnitude reduction in energy. So with that one example, I want to talk more generally about the future of this space. And my conclusion is that the future is going to be about designing these hardware accelerators for a whole bunch of applications. And you're not going to see an accelerator for each application. You're going to see accelerators which can do a class of problems. So for example, they can do image processing pipelines very well, or they can do convolutional neural networks very well, and so on. And you're also going to see specialization for a platform. For example, you're accelerating the same convolutional neural network, but the requirement for doing that on a mobile device versus doing that on a server are very different. So for example, on a mobile device, you care about energy a lot, whereas on a server, you care about throughput, whereas in a car, you care about latency. So based on whether you want most energy efficient design or most highest throughput design or lowest latency design, you're going to have different hardware architectures. And so you're going to see specialization in that sphere. I'm going to sum up where efficiency comes from when you design these accelerators, and that also sort of leads to what to look at when you're designing accelerators. So one of the biggest things where efficiency comes from is from modifying the algorithm itself. So as we saw for deblurring, you look at where you can exploit sparsity, you look at where you can reuse computation. So basically, not just taking an algorithm and mapping it as is, you basically have to drill down deeper into what the algorithm is doing and figuring out ways where you can reduce computation. So modifying the algorithm at different levels such that it becomes well-suited for hardware implementation. And that also, another side note to that is that sometimes hardware is it's good at doing certain things, so you want to do more of what the hardware is good at and less of what the hardware is not good at. The second place where efficiency comes from is basically reducing instruction overhead. So normally when you have a processor, you have to issue an instruction for an add, for a multiply, for a load, and so on and so forth. If you have an accelerator, for example, if you have an accelerator for video decoding, you basically have one instruction, which is called decode the next frame. And decode the next frame does a truckload of work. So basically, you're reducing the amount of instruction overhead that you have, and that leads to efficiency. So one is that. So, and then for each instruction that you do a lot of work in parallel. So for example, for the correlator, we saw that with one instruction, we were operating on multiple data. And then there are things that I didn't talk about, which is reducing precision, which is very important when you're designing hardware accelerators. For example, most of these accelerators don't work with 32-bit floating point values. They work with 8-bit or even smaller precision. And so that's also something where efficiency comes from. And you have the flexibility of designing a memory hierarchy that's very right for your problem. And so these are all the places from where you get this 3 orders of magnitude improvement in efficiency. However, there are a lot of challenges associated with designing accelerators, and the biggest challenge is algorithm architecture co-design. So basically, we're in a place where you cannot either just take the hardware as is that's given to you, or you can design hardware as an afterthought. So you focus on designing the algorithm first, and then you think, OK, now I want to make a hardware implementation for this. It basically has to go hand in hand. So you want to be able to figure out, at the time of your algorithm design, how would non-CPU or a non-GPU type of hardware deal with this algorithm. So for example, if you're designing neural networks, right, you want to think about precision. If you can manage to do your algorithm in small precision, 4 bits or 8 bits, there are many efficient hardware accelerators that you can then use to do your algorithm. So it cannot be an afterthought. You have to think about hardware while you're designing your algorithm. There are very open challenges about the programming model for such things, because there is no standard, and that's something that I want to work on in the future. And then if you're going to go about designing accelerators for a whole bunch of applications, you have to figure out how to lower the design costs, because accelerator, like if you want to design one chip, it is going to take you 2 years to design that chip. So this is also something that I'm interested in working on in the future. So I'll end there, and I'll appreciate any questions. Thank you.
Somebody must have a question, right?
Sure, I'll ask.
Yeah, okay. Thanks, Steve.
So tell us more about the connection between hardware and software in finding solutions. It seems like even when you have dedicated hardware, our software needs to be aware of that. And,
Yes.
and maybe related to that, although you focused on dedicated hardware, what about things like FPGAs and software reconfigurable hardware? Does that compete with dedicated hardware solutions?
So so FPGAs are great. The problem is the amount of time it takes you to do an FPGA design is almost as much as high as the time it takes you to design a dedicated accelerator, because you have to go all the way down to Verilog for programming that FPGA. There's hope with high-level synthesis tools, both on the ASIC design side and on the FPGA design side, to reduce that design time. FPGA does give you the flexibility of changing your hardware on the fly, but then it comes at an energy cost, because all the wires are programmable. So it's orders of magnitude less energy efficient than ASIC. So basically, you have to see whether you can tolerate that energy cost. If it has to be deployed in a mobile phone or an IoT device, it might not be the best possible solution, but something for the server, sure. Yeah. The other part is, even when you have a dedicated accelerator, the mapping problem is very hard, and that's something that I want to address. So when I talk about programming model, or even to generate the configuration for that hardware accelerator, it's a hard problem, and so there's already some work in that direction, but it's something that I want to work on in the future as well.
Hi, quick
Yes.
questions. So you are proposing more specific ASICs. However, even nowadays with FPGA, we're having difficulty communicating using a programmable interface. Each hardware vendor, they have pretty much no incentive to provide a general, let's say, NVIDIA,
Yes.
Intel,
Yeah.
Xilinx. OpenCL is out there for a couple years. This general support is still here and there.
Yeah.
They have no incentive to sell a generally acceptable interfaces.
Yeah.
And now introduce a significant cost for the software side to adopt a certain ASIC. And if we adopt a certain ASIC and we implement it, it's even harder for us to change for next generation ASIC if there is
Yes.
a protocol incompatibility. Is there, do you see that going to be changed since there's money in there for the
I think it is going to change because there's incentive now for specializing. So I think there would be more and more drive towards standardizing some of these interfaces. But yeah, it is definitely a problem and needs to be addressed. Yeah.
Great.
Thank you.
Thank you very much.